Ready.
Of course. All right. I'm Cassandra, and we'll be going over our Wildness Index web map tonight. Next slide, please. So our team members included myself, Luke, and Michelle, our sponsor, Victoria Jarvis of the Society for Wilderness Stewardship, and also Julia Cotter, who joined us as well. And then Sky was our UW steering committee. Next slide. All right, so tonight we'll be going over a description of our project, a definition of wildness, our strategic implementation of it, the map itself, the risks and challenges, and then the lessons that we learned. Next slide. All right, so the Society for Wilderness Stewardship is a 501c3 nonprofit promoting excellence in the professional practice of wilderness stewardship, science, and education to ensure the life-sustaining benefits of wilderness. And then over on the right, we have a definition of wilderness, but we'll be going over that a little bit more in depth on the next slide. But our task from them was to develop and design a web map using ArcGIS Online that assessed lands within the state of Washington, both private and public lands, under a wildness index utilizing multiple parameters. And the parameters that our group came up with was ecological intactness, human footprint, and natural systems. We aggregated these together into a value, and then we kind of color coded it into our final wildness index. Next slide.
Great. So kind of our first task, as Cassandra alluded to, is figuring out what this concept of wildness even is. So in front of you is a figure of the continuum of wildness. And basically, wildness increases as a function of both its naturalness and its freedom from human control. So you can kind of see that the more controlled and artificial a particular landscape is, the less wild it will be, whereas the more self-willed and pristine the landscape seems to be, the more it slants towards wild. So we've got a couple attributes that compose this concept of freedom, and that is the degree to which land provides opportunities for solitude, similarly the remoteness of the land from mechanical devices, and then the degree to which ecological processes remain uncontrolled by human agency. And the other component of the continuum is the attributes of naturalness, and that's the degree to which the landscape maintains its own natural composition, as well as the degree to which it remains unaltered by artificial human structure, and hopefully it's unpolluted. So then our next task in the project was kind of figuring out how to translate this concept to an actual map. So what we started with was 10 indicators or data sources. Some of those were selected by the sponsor, and then the other ones we actually located as a team. And the idea behind these 10 indicators is that they would reflect those key attributes of wildness. Next, we grouped all of those indicators into 3 different sub-indices. Those are ecological intactness, human footprint, and natural systems. And so within each one of these sub-indices, we weighted the importance of each indicator based on its importance. And that importance rating was kind of determined by our sponsor's expert opinion. And then once you overlap all 3 of those sub-indices together at the kind of intersection is where we obtained our wildness index. And each sub-index was ultimately weighted equally in the final aggregation. So we were starting to lay the groundwork of the actual project itself, and then we started to wonder how we're actually going to do this. And so in front of you, we have 10 different snapshots of each one of the data sources that was ultimately used in our wildness index. You can see that they range widely in data type. We have both vector and raster data. Some of the data sources are already composite indices. So on the upper left side of the slide is the Resilient Land Mapping Tool, as well as Climate Atlas Map. And both of those are already composite indices that we wanted to bring into our analysis as well. We also had vegetation departure, a map of Washington state highways, a map of interpolated air quality data points, trail systems, water quality data, priority habitat and species distribution, light pollution, and then human development. So within the state of Washington, we had quite a breadth and depth of different types of data that we were trying to bring together into one analysis. The primary ask of our sponsor was to ultimately put this together in a raster map. So we started with something that looks similar to what's on the screen here. The green layer is the interpolated air quality data broken down by county within each within Washington state, and then overlaid with the blue layer are the reclassification of water quality data. And so we were like, okay, let's put this together on a map and run it through raster calculator. And this is all that we got. One of the challenges was that some of our data sources were only point or line data, right? So we had a difficulty trying to figure out how to turn this rasterized process into something that would encompass the entire state of Washington. So that inspired us to pivot slightly into a new geodatabase design. We leaned on one of Mark's suggestions, which was to use the Calculate Composite Index tool, which is part of the Spatial Statistics Toolbox. And this is a really powerful tool that even Esri had put out a publication on the far left side of the slide called Creating Composite Indices using ArcGIS Best Practices. And we ended up leaning heavily on this guide. It's like 40 to 50 pages. And kind of the foundational principles behind that guide is helping users develop an index in a responsible way that actually represents the data at hand in a way that makes sense and actually is responsible to what its true meaning is. So you can see on the bottom of the slide, there's a little bit of an illustration of this Calculate Composite Index tool. On the far left in the pre-processing sort of category, each one of the variables is totally different. It's on a very different scale. And part of what you need to do in order to use this tool is actually process that data into a standardized rating system so it can ultimately be run through the tool and aggregated into a composite index, like the post-processing image of that map. As part of our project, we put together some really comprehensive documentation because part of what our sponsors asked was to basically create a pilot in hopes of determining the best methods moving forward to kind of create a map like this, and something that they could ultimately expand in scope from just the boundary of Washington to hopefully the entire United States. So there's a couple screenshots of our methods documentation as well as the appendix, which includes all of our very in-depth detailed instructions with screenshots of everything we did to come up with our final product.
Yeah, so like Michelle said, we were pretty lucky, and thanks to Mark also for pointing out the Calculate Composite Index tool. We had initially thrown together a pretty rigorous mathematical formula that we were planning to go through, obviously not by hand, but not necessarily in ArcGIS. And well, that would have been or we thought that would have been fairly straightforward, that it certainly would have taken a lot more time. So once or rather I should say, we did quickly find out though that this tool, the Calculate Composite Index tool, does come with a set of prerequisites that you need to meet before it will run the way you really want it to. And in that article that was on the last slide, it calls it pre-processing your data. So, Cheryl, if you could hit the next object. Yeah, so just to give some examples of how this entire process would go, we could start out with, one data layer that we might have from NASA would be the entire US, or at least it was the continental US. Others were already just Washington. There was also a layer we had for protected habitats that would have boundaries that would spill over into Oregon or Idaho. So we basically would always start out with something that wasn't quite what we wanted. And the process to get each layer to where we wanted it to it had some similarities, but a lot of them are quite different, actually. However, it would mostly start off with, for example, just clipping the feature to a mask of Washington State. We made sure to use the same mask for all layers because it has to be uniform. And then once that was done, yeah, if you can keep going, right. So this is just another example of how, the data, you might have data from different sources that might not match up. And so what we ultimately decided to do to fix that was to basically fit all the data layers we had onto US Census tracts. Counties in Washington are too big, it wouldn't really be very useful. And we figured the smallest unit we could go with that would offer really sort of granular data would be census tracts. So that's what we picked. From there, we also made sure to find the same Washington State census tract layer, and you could use that to extract what we needed. But that would be very different depending on which layer we were working with. So ultimately, what we wanted to end up with was one table that had data from all layers in it. So in order to get there, typically what we would need to do is use something from either analysis tools or image analyst tools. That could be summarize, thin. We also used it. Some layers involved using a portion polygon. Some of the rasters needed to be reclassified. I think you can click once more. That might be yeah. And finally, I think the tool that really helped us out the most was zonal statistics as a table. So that actually wouldn't output a new layer, but it would just give a summary of all the statistics that it can based on a base or input layer. Of course, we use the census tracts for that. And the output would be a table. And so the idea, once we were finished with any one layer, would be to have to have data that basically that was broken down into individual census tracts. And then final sort of steps would be to join, either spatial join or just join field. It's kind of shown here. And thankfully we could use the FIPS code, which is just the code for each individual census tract, since that would be in all of our tables at that point, to join all of them together. We actually did do this step by sub-index individually. So one had just had 2 tables, one had 3, and one had 5. So for some of them, tables at the end would be quite long and kind of unwieldy, but ultimately we got the data we needed. I think there's one more object on this page. Yeah, it's the semi is the last one. So as it shows here with the state of Georgia, we just did for Washington. We eventually got everything into tables. It shows variable 1, 2, and 3 here, just as an example. And then you could just run the composite index tool to get what you needed. I think, yeah, from there we can go to the next slide, I believe. Yeah, so connecting concept to analysis. This is what the toolbox, or sorry, the tool looks like within ArcGIS Pro. You can see we've got some examples here. We've got a composite table that we had to put together for human footprint, and the individual variables that we were putting into this index were median natural breaks class, trail mileage, highway mileage, and there's also, well, you can see there's next to it a tick box for reversing direction. So what that is there for is to just, as an example, So you're working with the protected habitat layer. In that layer, the higher the count, more protected habitats, the more wild it is. However, in say the water quality layer, the classification that is used by the state is actually, it tops out at 5, with 5 being the most polluted. So in that layer, the higher number is less wild. And so this just kind of illustrates how important it is to keep things like that in mind, to really understand the data you're working with beforehand. Because if you put just all the fields in there you want to use without making sure that something like reverse direction is ticked when it needs to be, you'll just have data cancel each other out in one way or another when you don't want it to. And then there's a couple other presets here, but you pretty much stuck with what ArcGIS wanted to, ArcGIS Pro wanted us to. But the one here that was mentioned earlier is the variable weights. And we just kind of talked through how these were decided. So the top variable is the NASA Global Human Buildup and Settlement. And that was already a composite index that NASA had put together. And so since that already, I mean, it goes a long way to representing what we were already looking to find. So we wanted to weight that quite heavily, and we gave it a 60%. And that's reflected in the weight column there on the left. And the next two are roadways and state trails. Roadways, we obviously weight a little bit more, 30, and trails, which is 10. Hopefully that seems kind of intuitive. You know, a highway running through somewhere is obviously going to make it less wild than just a state park trail. So that's kind of how we ended up with those weights, and it's reflected in the same two other sub-indices. I think that's what we've got for that one.
Right. So in addition to our wildness index, we also wanted to provide our sponsor with a referenceable base map to visually depict owned and protected land as a background for users of our finalized index. So I was able to find 2 data sources that I really think kind of help with this. The Protected Area Database by the USGS, and then Wilderness Areas in the US by Wilderness Connect. Next slide. So I was able to bring these 2 layers together into a map of Washington. That way people can kind of see, like, as a general overview, here are the areas in the state that are owned or protected in some way. And then once they click on the area, they can see more information about it. Next slide.
Okay, and now we're gonna share our map demo. This is the Wildness Index web map walkthrough. In front of you, we have the state of Washington broken down by census tracts, which was used as our polygon join to generate our composite wildness index rating. In the legend, you can see that there are darker blue hues to lighter blue hues. Darker blue indicates more wild, lighter blue indicates less wild. We have 2 layers in our web map. One is the wildness index, which you're currently viewing, and then at a more fine scale, we have the reference map that will be displayed. Here's an example of what our web map can do. When you click on a census tract at this statewide scale, you just generate the wildness index pop-up window, which is a scale of 1 to 10. 1 being most wild, 10 being least wild. We did this because we measured everything in terms of peak degradation. There are 1,772 census tracts within the state, and so each census tract is ranked in terms of its wildness. In this pop-up window, for the census tract, it is ranked as number 1, so it's the most wild census tract in the entire state. We can scroll down through the pop-up window to get a little bit more in-depth information based on how this census tract performed on the statistical analysis of the Calculate Composite Index tool, which is broken down by each indicator that was used. The black line for each indicator is the mean or the average of how all census tracts in the state measured up for that indicator, and the gray bar is how this census tract in particular measures on an indicator. So you can see that there's a couple indicators where this census tract populated a value, but there are also several indicators where no value was even assigned because the statistics was so low. And when we zoom to this particular census tract, we start to populate some more information with crosshatching and darker and lighter green hues. The user can toggle around within this census tract to get a better idea of what sort of parks and protected areas already exist in this census tract. In this particular example, it makes sense why it would have been ranked as number 1 because this is within the North Cascades National Park. Next, I'm going to show you a more urbanized setting. One of the asks from our sponsor was to also be able to identify areas that were outside of parks and protected areas to determine what sort of degradation was occurring in any given census tract and identify potential routes of improvement to improve that score. So we have in front of us the Seattle metro area. You can see that there's a wide variety in terms of colorized ranking systems, from that darker blue hue, which indicates more wild, to also lighter blue hues. So I'm going to zoom to one census tract I identified in particular. This is in the Berrien area. I was curious about this census tract in particular because it has no parks and protected areas, and I was curious what sort of information we could glean using our wildness index. So this census tract in particular indexes at 8.82, which is actually above the statewide average of wildness rating. You can see how it falls in terms of ranking system, and we can kind of scroll through and see how the gray bar in most indicators was above the average. So this gives us a little bit of information from a management perspective, from an advisory perspective, to potentially make recommendations on how to improve the wildness of this particular census tract. The last thing I wanted to demonstrate was one of the charts that we generated for this map. And this is the number of census tracts by wildness index rating. And so this is a useful tool. It gives us an idea of the spread of wildness index ratings over the entire state. You can see that the mean mean wildness index rating was 7.14, with just a handful of census tracts clocking in at the most wild sort of ranking system. So super useful information here. And what's cool about the web map is that on the fly, you can kind of calculate some more statistics. So we thought our sponsor might find that valuable. And with that, I'm going to wrap it up. Thanks for watching. This is the Wildness Index.
Yeah, so we ran into a few challenges while we were doing this. First, obviously, as you can see, is to pick which data sources we wanted to use. This kind of came with the inherent risk of, maybe the ones we wanted to use or we thought were most representative of wildness weren't always the most easily accessible. So just as an example, Washington Department of Fish and Wildlife, I had a map that we really needed to use, but according to the website, we had to call their office and request a PDF be sent to us, and they did not seem to be regularly open during the hours they suggested. So we had to resort to a number of different tactics in order to get the data we wanted. And even, in some cases, I think, or the most extreme case, I should say, would be, you could find an image of the data we wanted. Then we'd have to take a screenshot of it and then georeference it to fit with the rest of it. And even that time would, if you do something like that, I don't think it's up here on the screen yet, but you can imagine that screenshots will include things like labels, and that's not something you want included in in computing the wildness index. So we have to be careful of those kinds of things. In addition to that, I would say on the whole, the largest problem we ran into was during that pre-processing phase for the data that I mentioned earlier. I mean, no two data layers that we had looked alike. Some were vectors, some were rasters, some had to be imported, as I said. And then, let's see. Yeah. Another issue was that, because they were so different, I was able to walk you through a kind of generic method for what we did earlier for one data layer. But really what that meant was that there was no automation possible for this. It kind of would have been nice to be able to write a Python script or something along those lines. But given the data that we had, that really wasn't feasible, or it would have ended up taking much more time ultimately. So yeah, then finally it was it was a while before we realized that ultimately we want is either zonal data or vector data for the composite index tool to run. We had to decide on census tracts. And we got kind of, by the time we had this all worked out, it was a bit later in the schedule than we were hoping. So that all compounded a bit to present a few challenges for us. I also mentioned earlier things like making sure the data aligns as it points in the same direction. That in itself isn't that complicated, but it does sort of represent the type of knowledge you have to be aware of and thinking about the whole time while you're putting this together, because something like forgetting to check that tick box basically ruins the result. Yeah. So, and I mean, all this together basically combined with the fact that, of course, like everyone else, we had limited time and resources. I mean, that ultimately was what sort of felt like the most crucial thing that we kept running into. I believe that covers most of it for this slide.
Great. So we have a couple of reflections and suggestions for improvement for the sponsor going forward and things we would probably change. I think that after the project was said and done, we realized that it might make more intuitive sense if 10 was most wild and 1 being least wild. So I think if we were to do the entire project over again, we might have reorganized that. So something to tuck in our back pockets for next time. And then I think as well, we ended up using census tracts as our polygons to join all that data to run this zonal statistics by table tool. But ultimately, I think there's something better. And we got this suggestion from Sky after we kind of started building our database. So next time, what we would suggest is using the generate tessellation tool, which is under the data management toolbox. And what's really neat about this is that you can generate your own polygon layer in whatever shape you want. We watched a John Nelson video about it, and he swears by transverse hexagon. He says that is a super trendy shape right now. And if we were to reprocess our project using a transverse hexagon polygon, we might get something that looks a little more like this, which would be a more fine scale sort of cookie cutter shape that we'd be able to join our data to. One of the challenges with census tracts, as we all know, is that they're predicated on population density. So a lot of those rural areas got generalized at a very large scale, whereas more urban centers had a little bit more fine-tuned information. So this is something that I think could be looked to for the future to kind of get a little more fine scale information about wildness in especially rural areas. In addition to that, I think another suggestion we would point out would be making sure that all of the data sources we use cover the entire state of Washington. So instead of using point source data for water quality, looking towards something like watersheds, which encompass the entire state itself, might provide a little bit more information on beyond just the specific, rivers and lakes. And lastly, some of the future things that we are going to pass on to our sponsor for considerations are experimenting with the variations in the pre-processing. I think Luke gave a really great sort of explanation of all the transformations we had to go through and in terms of weightings and how we combined things. And I think there's a lot of adjustments that could be made to refine some of the takeaways ultimately with the map. So that's something they can look into. And then similarly, investigating the spatial clustering or kind of like hotspot analysis within the state to determine, where there's more wild areas versus areas where there's more potential to become more wild. And then lastly, I think Luke said it best, it would be ideal if we could have built some sort of automated, model builder tool to help us process the data, especially during that heavy lift phase of the pre-processing. I think now that we understand the different categories of types of data in our map, we would have been able to build a model builder in hindsight, but at that phase, we were still just building the plane as we were flying it. So hindsight 2020, but I think there's a lot of potential to refine what we've created. And these are a couple suggestions. And lastly, here are the sources that we leaned on to create the map. And we'd like to open it up if anyone has any questions. Thank you so much. Yeah, Megan.
You know if anyone else has done anything like this, and if not, do you suspect that this will expand to different states? This I should preface this by saying this is so cool. This is really incredible. So just curious if there was anyone else doing this.
Oh my gosh, I'm so flushed. Thank you for the compliment, truly. I think there are some maps similar to this in some ways, but nothing quite like this. So I think that was part of the unique opportunity we were provided with this project, was that it's kind of a gap in information. As far as I understand it.
Yeah. Do you see it spreading?
Yeah, I think our sponsor has hopes to spread it across the entire United States. So this was kind of like, let's do it on a small scale, right? Which Washington is still huge, but then hopes to kind of like expand it. I think the limitation with that would be finding national data sets, especially in a time of maybe we could call data insecurity. That might be the biggest threat to expanding it. But yeah, hopefully.
Cool. Thank you.
Yeah, we've got a few other. We'll go Cody and then Olivia.
Did any of the areas of analysis kind of surprise you in the analysis outcomes?
Yes, but to be honest, I'm having a bit of trouble remembering which ones they were off the top of my head. I just do remember getting some of the results and thinking that didn't quite make sense. But then looking closely, oh, I do remember now what it was. This isn't that groundbreaking, but when looking at the air quality layer, we had to pick whether or not we were going to use the median air quality index for our data or total number of good days throughout the year as the individual data that we wanted to use. And I do remember finding it interesting that most of the counties, well, I guess first of all, I should say that, you would have thought that median air quality index would be a great way to do that. But in fact, when you're, I don't want to say average, but when taken over the course of the entire year, that doesn't give you a whole very useful range. In fact, most of the state kind of just ends up being fine. And with like obviously downtown Seattle, or rather like the port of Seattle being pretty good, and of course national parks being pretty bad. But So we ended up using total good quality days for that. But I do remember finding it weird that I think the best air quality in the state were those, I can't remember their names. One is Asotin County. I think those 3 slender ones in the southeast. And I kind of expected it to be, North Cascades or Olympic National Park, but a couple of those were actually ranked higher. Just an example.
All right, Olivia.
This was incredible. Like, wow, this is so cool. Just amazing work. This is, I guess, more of a comment than even a question. I love the little charts in your pop-ups of the little scale bar in the pop-ups. And you don't have to explain that right now, but I would love to know how you did that. That's so cool. I really enjoyed that.
I wish we could take credit for that, Olivia, because I was like, ooh, dang, those are cute. But I think it's actually just part of the tool itself when you upload it to ArcGIS Online. But that's magical in itself.
It's so cool. I am so proud. Well, the whole thing, but like those little charts, so cool.
I have to say, I agree. I think there were some really great observations, and I'm really glad that those tools actually came through for you, because I know that we kind of bounced around on them initially. So this is really, really a cool outcome. I'm happy you got to where you got with this. It looks really cool. And I do like that you thought about kind of the observations with the density of census tracts, right? And how that can really affect that too. That's really forward thinking and well thought out. So it's good to especially note that and think about that for the future with your sponsors. So I mean, overall, it looked really great. I'm happy with the final product. Great work, all of you.
Yeah.
Thanks.
Any other comments or questions for the group? All right, I'm going to stop